then at the University of Chicago. I am a student of Nobel laureate -1. U condenser. Harold Urey, synthesized, organic compounds under conditions resembling the primitive atmosphere of the Earth. At that time it was believed that the Primi 5 type atmosphere had probably been composed chiefly of water, vapor, methane, hydrogen and ammonia, latter 3 in the pipe _SR ratio of 1:2. Such a gas _5 containing mixture was circulated through a amino acids closed apparatus by steam from boiling water and subjected to an electric spark discharge, 75,000, figure 12.4. The spark charge apparatus of Miller for producing organic volts between tungsten electrons from a reducing atmosphere. Trodes, figure 12.4. The electric discharge duplicated the effects of violent electrical storms in the primitive universe. The gas mixture was then condensed and added to the boiling water for recirculation. Any non-volatile substance that appeared would accumulate in the water. This apparatus was permitted to run for a week. The results were spectacular. Several amino acids were synthesized, e.g., alanine, glycine, glutamic acid, aspartic acid, valine and leucine, in both DAND-L forms, and a number of other organic compounds, such as hydrogen cyanide HCN, aldehyde and cyano compound C=N, appeared. About 15% of the carbon in the gas mixture became incorporated into these compounds. Miller's instructive experiment has been successfully repeated by a number of investigators. Amino acids can also be generated by irradiating a similar gas mixture with ultraviolet light. Both purines and pyrimidines can be formed when HCN and cyanoacetylene C=N are present in the gas phase of the Miller-type reaction. HCN is reactive in the presence of UV light alone. N 500 milliliters flask containing boiling water. Origin of life 147. Purines, mainly adenine, can be regarded as condensation products of 5 HCN molecules, although the route of synthesis is still not clear. Miller and Orgel, 1973. Polymerization of HCN also gives rise to orotic acid, which can be photochemically decarboxylated by sunlight to pyrimidine, uracil. Even ATP can be formed under prebiotic conditions, especially in the presence of the common mineral apatite, calcium phosphate. Protenoid microspheres. The synthesis of monomers, e.g., amino acids, is only a small step toward the synthesis of a living cell. In 1964, Sidney W. Fox, then at Florida State University and later at the University of Miami, reasoned that proteins were synthesized from amino acids in the primitive Earth by thermal energy or heat. Fox accordingly heated a mixture of 18 amino acids to temperatures of 160 to 200 degrees C for varying periods of time. He obtained stable, protein-like macromolecules, which he termed protenoids. These thermally produced proteinoids are similar to natural proteins in many respects. For instance, bacteria can actually utilize the protenoids in a culture medium, degrading them enzymatically into individual amino acids. Equally important, when the protenoid material was cooled and examined under a microscope, Fox observed small, spherical, cell-like units that has arisen from aggregations of the protenoids. These molecular aggregates were called protenoid microspheres. Physical properties of protenoid microspheres. The protenoid do micros_spheres resemble the earliest CGLLS_. Microspheres were spherical. Mercurel_ERN_UCORS for _S can be F-formed by agitating protons AR_1DNXX greater than X lipids in a liquid medium. Such microspheres can take in material scopic and of uniform diameter. They're from the surrounding solution, grow, and even reproduce. Size remained in between the range of 0.5–0.7 mp diameter. They had a number of properties in common with coccoid bacteria and microfossils found in ancient geological strata. Fox, 1969, in containing uniformity in size, stability in centrifugation, electron microscopy, extreme pH variations, etc. Structural properties of protenoid microspheres. Electron microscopic studies of protenoid microspheres have revealed concentric double-layered boundaries around them through which diffusion of material from the interior to the exterior occurs. Further, protenoid microspheres has the ability of motility, growth, binary fission into two particles, and a capacity of reproduction by budding and fragmentation. Further, some of them are stainable by gram-positive stains, others by gram-negative stain. Enzyme-like activities of protenoid microspheres. They are found to have catalytic activity, such as degradation of glucose, and this enzymatic activity of them is partially lost during heating. The model of protenoid microsphere for protocells is widely accepted because of its following significances. 1. Such protenoid microspheres arise from monomers, rather than from polymers obtained from organisms already in biota, as is true for the usual experiments with coacervate droplets. 2. This model suggests that protenoids are informational, and it shows the origin of communication, which may be intercellular or intergenerational communication. In fact, it suggests the simultaneous origin of both types of communication. Since both proteins and nucleic acids, plus other simpler substances, are required to develop and reproduce organisms living today, an obvious question is which of these substances arose first. No clear answer is available. To date, protein-like materials have proven easiest to synthesize prebiotically. Perhaps they arose first. This implies that there was some sort of replicating genetic material associated 148 evolution evolutionary biology with early proteins upon which selection could act. This replicating material could have been a protein itself. It is difficult to say that this is impossible, but no self-replicating proteins are known. J. W. Valentine, 1976. Nucleic acids seem difficult to form, but they do replicate. Perhaps the earliest gene was a simple nucleic acid, i.e., RNA. The trouble with nucleic acids is that they do not do anything themselves. This paradox has been recently resolved with the discovery of a catalytic RNA by Czech, 1982-1986. At this stage, let us analyze the following models regarding the first genetic substance. 1. Cairns-Smith's model. The model of primitive genetic system proposed by Cairns-Smith, 1971, postulates that the first genes were minerals, minute crystals associated with proteins as concentration sites and to some extent as templates. Certain minerals, e.g., clay or other layered silicates, were in very large supply as products of early rock weathered. They might have favored the formation of classes of polymers for which they provided good templates. Natural selection would favor a polymer whose activities preserved or even increased the supply of its mineral template, perhaps by helping to weather a parent material to produce the clay gene. The association of two, and eventually many, different polymers might have aided in mineral formation, while others provide adhesion for the polymer colony, and still others cleaved prebiotic organic compounds to provide building block materials for the colony, and so forth. The polymer in any such early colonies would have proteins, but eventually a nucleic acid was added to a colony, presumably for some property other than protein coding or even self-replication. Perhaps its original function was mechanical, acting as a fiber or in some other structural capacity. This would be a very early example of pre-adaptation. The ability of the nucleic acid to code for proteins that were themselves useful to the colony eventually became manifest. Once the nucleic acid was contributing to colony fitness, any process that would replicate it in situ would be considerably favored. Thus, a nucleic acid, probably a simple RNA at first, would replace minerals as genetic material. Presumably, the nucleic acid gradually took over the task of coding for all the proteins employed in the colony, including those associated with its own replication. Eventually DNA evolved, presumably coded by RNA originally, and an essentially modern nucleic acids, protein system of gene, enzyme was present. At some stage membranes were developed around the colonies and those membrane-bound units became cells. Thus, according to this model, genes evolved in the following way. Clay genes, RNA genes, DNA genes having proteins. Cairns-Smith scenario is highly speculative. Evidence are lacking which may prove that life followed such a proto-adaptive pathway from prebiotic materials to living cells, see Valentine, 1976. 2. RNA first model. In recent years, evidences are in favor of RNA to be material of first form gene. Woese, 1967, Crick, 1968, Orgel, 1973, 1986, Watson et al., 1986, Darnell et al., 1986. Thus, a number of protein-free, i.e., non-enzymatic, reactions that could have been decisive in the development of the first biologically important polymers have been discovered by molecular biologists. These reactions include I. Formation of RNA oligonucleotide from activated monomeric precursors, E. Template-directed RNA synthesis, E. Site-specific RNA cleavage with and without the aid of second RNA molecule, and IV. RNA splicing. Thus, RNA may have been the first polymer and some form of reverse transcription may have given rise later to DNA. How the coordination between the RNA oligonucleotides and amino acids or peptides occurred remain unknown, but the result was a single universal three-letter code that is still used by all cells today. Further, comparison between the rRNAs of many different cell types as well as comparison between bacterial rRNAs and rRNAs of organelles, mitochondria and chloroplasts, have suggested two important conclusions about evolution. I. The overall two subunit structure of ribosomes is universal. 2. Secondary, stem loop, structure is extremely similar in all rRNAs. Thus, ribosomes can be considered as highly preserved but fairly complicated early cellular structure. Catalytic RNA. The precursor of rRNA of the ciliate protozoan Tetrahymena was found to contain a self-splicing intron containing 413 nucleotides, which acts as an enzyme, i.e., it excises. Origin of life 149. Itself from the rRNA precursor without the help of a protein enzyme, Czech and co-workers, 1982, 1983, 1986. The ability of rRNA intron to function as enzyme implied that the very first living molecule might have been an RNA replicase that catalyzed its own replication without the help from a protein, see Watson et al., 1986. The discovery in 1983 of a second catalytic RNA species, 377 nucleotides long RNA component in RNP or ribonucleoprotein, of E. coli lent strong support to this notion. In streak virusoid, Lucerne transient, 2 RNA enzymes work like protein enzymes, Pace and Marsh, 1985. Catalytic RNA are now considered as molecular fossils whose history dates back to the earliest life forms. Thus, the discovery of intervening sequences, the introns or junk DNA, mainly in the eukaryotic genomes, has given rise to much speculation about the nature of the earliest genes. Because protein-free RNA reactions include cutting and splicing, and because splice gene structures are relatively well preserved over enormous evolutionary intervals, i.e., more than a billion years, it is possible that the first gene had non-contiguous coding regions and that splicing was a prominent feature of the most primitive genomes. According to this view, cells lacking introns may have lost them due to selective pressures associated with rapid growth, whereas eukaryotic precursors were slower growers that did not lose their introns. The antiquity of the eukaryotic lineage is supported by the rRNA lineage studies, see Darnell et al., 1986. Why RNA and not DNA was the first living molecule? New examples of RNA molecules with enzymatic activity are constantly being discovered, but no enzymatic activity has ever been attributed to DNA. Further, ribose is much more readily synthesized than deoxyribose under simulated prebiotic conditions. Process of origin of life. With such a historical background about the speculated modes of protobiogenesis, now we are in better position to discuss the present current understanding of molecular evolution and its culmination into the origin of life. The prerequisite for the treatment of the problem of protobiogenesis is the origin of the raw materials, matter, elements, stars, planets, etc. For the molecular evolution, viz., a brief introduction of cosmology. 1. Structure of cosmos. The universe or cosmos is made up of countless aggregation of stars organized into systems of various shapes and types, called galaxies. These galaxies, each of which includes hundreds billions of stars with their accompanying planets and satellites, are distributed into the vast reaches of space. Milky Way is a galaxy which is composed of 100 billion stars besides Sun and its planets, viz. Solar System. The Sun is a star being 5 billion years old and remains in a rapid state of motion. The planets of Solar System are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune and Plato. All the planets of Solar System rotate around their axis and revolve around the Sun in elliptical paths determined by the gravitational force. 2. Primitive Earth. It is a tenable hypothesis that the cosmos as we know it originated in gigantic explosion, Big Bang hypothesis of Avi Lemaitre, 1950, which blew matter from a primordial fireball, scattering outwards the materials of the universe in an ever-expanding volume. Clouds of dust and gases, chiefly helium and hydrogen, spread through the space, thinned in some regions and dense in others. Stars can be formed from the condensation of such clouds. Our own sun probably formed from a rotating mass of dust and gas that was flattened by the spin and which collapsed upon a central region due to the force of gravity. As the gaseous disk condensed inwards, the spin of the central region must have increased in order to conserve momentum. At some point the spin could have become so great that material would be ejected owing to centrifugal force. However, as such a point was approached, and the centrifugal force increased, matter in the outer portions of the condensing disk would tend to be more 150 evolution evolutionary biology. Attracted to local dense patches than do the central region. Thus, at some distances from the proto-sun, matter would be condensed into separate bodies. These would be the planets, which lie in the plane of the sun's rotation. The solar satellites, including the Earth and presumably the other planets and asteroids and the Earth's moon as well, appear to date from about 4.6 billion years ago, see Valentine, 1976. 3. Prebiotic synthesis. The core of the primitive Earth melted from heat of condensation, but the outer crust cooled quickly except where convection or volcanic eruptions brought heat and mass from the molten core to the surface. The primitive atmosphere was formed as various gases escaped from the interior of the Earth, outgassing. The early gas cloud was especially rich in hydrogen, H. The hydrogen of the primitive Earth chemically united with carbon to form methane, CH, with nitrogen to form ammonia, NH, and with oxygen to form water vapor, H, O. Thus, the early atmosphere had a strongly reducing, non-oxygenic character, containing primarily hydrogen, methane, ammonia and water. Darnell et al. 1986 has, however, argued that these gases, or compounds, may not have existed free in the atmosphere in large quantities for extended times. Carbon dioxide, CO, and hydrogen sulfide, H, S, were probably more permanent constituents of the early atmosphere. The crust and atmosphere of the primitive Earth cooled slowly, and the first shallow seas were formed as the less volatile gases including water, rained back down to Earth. The oceans formed as a result of millions of years of torrential rains. The rains eroded the rocks and washed minerals, such as chlorides and phosphates, into the seas. The stage was set for the combination of the varied chemical elements. Chemicals from the atmosphere mixed and reacted with those in the waters to form a wealth of hydrocarbons, that is, compounds of hydrogen and carbon. Water, hydrocarbons and ammonia are the raw materials of amino acids which, in turn, are the building blocks for the larger protein molecules. Thus, in the primitive seas, amino acids accumulated in considerable quantities and became linked together to form proteins or oligopeptides. Prebiotic synthesis. Energy sources for prebiotic synthesis. Complex carbon compounds, such as amino acids and proteins, are termed as organic because they are made by living organisms. Our present-day green plants use the energy of sunlight to synthesize the organic compounds from simple molecules. What, then, was the energy sources in the primitive Earth, and how was synthesis of organic compounds effected in the absence of living things? It is generally held that ultraviolet UV rays from the intense solar radiations penetrating through the thin ozone-free atmosphere, electric discharges such as lighting from rainstorms and intense dry heat from volcanic activity furnish the energy for prebiotic synthesis such as joining the simple carbon compounds and nitrogenous substances into amino acids. Orgel, 1973. Superheated hot springs were also formed along rifts in the seafloor. Alternating cycles of cold nights and hot days too might have affected the prebiotic synthesis, see Watson, et al., 1986. Evidence that oxygen was absent in primitive atmosphere. The sedimentary rocks that remain from 3.8 to about 1.9 billion years ago, which appear to have been deposited chiefly in shallow epicontinental seas, generally suggest an anoxic atmosphere of the primitive Earth. The minerals are mostly in low states of oxidation relative to today, although more highly oxidized layers do appear locally. The most famous examples are the banded iron formations which contain vast amounts of ferrous iron. This indicates that free oxygen was not available in the atmosphere, otherwise the iron would be in a ferric state. Cloud, 1968. There are certain other considerations which show why the primitive atmosphere lacked free oxygen. Free oxygen is available in quantity from only two sources. One is photodissociation of water vapor, which occurs high in atmosphere. Hydrogen, freed from water molecules, leaks out into space, while the heavier oxygen is retained. The extent of this process in the past, and the rate at which photodissociated oxygen could accumulate, are much debated. Oxygen is also produced from water via photosynthesis. It is commonly believed that the bulk of free oxygen was produced by plants. Before the advent of life, and indeed until plant biomass became large, this source of oxygen was absent or unimportant. Origin of life 151. Evolutionary stage. Prebiotic synthesis. Polymer world. 4. Evolution of. Progenote procellular. Molecular and cellular events. Synthesis of essential. Monomer 3. BU1LL.